Hi everyone, my name is Gina and I work as an educator with the Mount St. Helens Institute. I'm excited this week to teach a little bit about plate tectonics and the science of volcanoes. Why do we have volcanoes where we do around the world, and how does that connect to the structure of our Earth and how our Earth is composed of tectonic plates on the surface? So to begin, I brought from my fridge an egg. This egg represents our Earth. The Earth is very much like an egg, as in there is a thin, hard, brittle shell on the outside surface, and on the inside there is material that is less solid, more liquid, not completely liquid. We call it sometimes a mush. Our Earth's crust is broken into pieces that slide and push against one another. The way that these pieces behave determines what we experience on the surface, determines where we have mountains, where we have oceans, and where we have volcanoes. We call the pieces of the broken up crust on the surface of the Earth tectonic plates. And tectonic plates can interact in a couple of different ways. Tectonic plates can slide against one another, they can collide into one another, or they can divide, getting pushed away from one another. I'm going to use my hands to model this. So again, tectonic plates can slide, collide, or divide. Now, volcanoes occur where the material underneath the crust, in the case of our egg, that would be the white gooey material inside the egg. When that material comes up to the surface, that material can come up in the form of volcanoes, and these volcanoes can come through where plates are dividing, that allows a space for that material to come up, and then also where plates are colliding. When two plates come together and one sinks down underneath each other, that can also cause some melting beneath the crust and cause an expression of volcanoes on the surface. But before we go there, let's take a look at a map of our world from space and think about if we can see any patterns of these plates on the surface. So here is a picture of our planet, and we can see the familiar continents and oceans. Looking at this map, we cannot necessarily see the different plates. I'm going to flip over to a view showing where these plate boundaries are. When we look at this map now, we can see that the plates somewhat outline the shape of the continents that we know, but not exactly. They do not exactly line up. I want to point our attention to the boundary between North American plate and the Eurasian plate. This boundary occurs in the middle of the Atlantic Ocean, and we can see the arrows here that this is a place where the two plates are moving away from each other or dividing. If we go back to our map of the world, and now we look in the center of the Atlantic Ocean, we see that there's a faint line there. That is a chain of underwater volcanoes that mark the point where the plates are dividing. Looking at that map of the world in 2 dimensions or even 3 dimensions, we can see the continents and the oceans, but it is still difficult to distinguish where the tectonic plate boundaries are. It's difficult to tell if some mountains are mountains and if some mountains are actually volcanoes. Yet if we look at how the Earth changes over time, that would be incorporating the 4th dimension, time, we can learn more about the Earth and its behavior and begin to recognize these patterns of where volcanoes occur around the world. So, we're going to look at a video to look at the patterns and help us identify the location of plate boundaries. This project was created by the Smithsonian Global Volcanism Program. What we're going to do is we're going to look at an animation that puts together data from every volcanic eruption that has occurred around the world since 1960. Before we look at the animation, I want to explain what we want to look for on the screen so that the animation makes sense to us. First of all, the map is dark colored. So if we look at the map behind me, you can see the faint outline in gray of our present day continents. On this map, there are 3 different colors. You'll notice that one of the colors is blue. The blue circles represent earthquakes. Earthquakes indicate volcanic activity, and oftentimes when volcanoes erupt, they create earthquakes, and so earthquakes are a great indicator. The earthquakes on this map are from magnitude 5 up to magnitude 9, so we are excluding some of the smaller earthquakes. There are just too many earthquakes that happen around the world to map them all. Larger circles indicate larger earthquakes, and larger circles likely indicate larger eruptions. That is what the blue circles mean. The next symbol on our map are the red triangles. The red triangles indicate volcanoes that are erupting. You'll notice already in 1980, the year that Mount St. Helens erupted, there were many other volcanoes erupting around the world. Small triangles indicate smaller eruptions. Larger triangles indicate larger eruptions. The final element on our map are the yellow circles. The yellow circles represent sulfur dioxide, which is one of the gases emitted by volcanoes. Volcanoes emit many other types of gases, including water vapor and carbon dioxide when they erupt, but the sulfur is easiest to detect in satellites, and so that is what the scientists put together to include on this map because it's an indicator of the eruptions. Again, small circles indicate smaller eruptions when the volcanoes were emitting less gases. Larger circles indicate larger eruptions. Finally, on the bottom of the map is a timeline. You can see that the timeline I have highlighted is May 1980, the year that Mount St. Helens erupted. If we look in the west side of North America, we can see a yellow circle, which indicates that is where Mount St. Helens had erupted, and at the time Mount St. Helens was still releasing a lot of gases. This is slightly after the 1980 eruption on May 18th, and so we can see there's a large yellow circle over Mount St. Helens. So the location of the blue circles for earthquakes, the red triangles for volcanoes, and the yellow circles for the sulfur gases all indicate places where volcanoes are active around the world. The next thing that we are going to do is we are going to take a look at this animation and take careful note to look for patterns for where we have earthquakes and volcanoes occurring. We're going to look at a video that shows all of the volcanic eruptions that have occurred around the world since 1960. When we look at this video, this will illuminate patterns of where volcanoes are occurring. Let's take a look. Here is the animation of eruptions that have occurred around the world since 1960. Notice how the time advances on the bottom in the timeline. Notice first the abundance of volcanoes and earthquakes that occur around the world every single year. Every day there are volcanoes erupting around us. Also notice that there's a pattern to where the most common and frequent eruptions occur. Notice around the Pacific Ocean there is a ring, and that ring has many blue circles and red triangles, indicating earthquakes and volcanic activity. Notice also where some of the largest yellow circles, blue dots, and red triangles are located. I'm noticing the largest eruptive activity is around this ring around the Pacific Ocean. This ring is called the Ring of Fire, and it is the place where the Pacific Plate is sinking under other plates. We can also see lines of other volcanoes and outlines of other plates with smaller volcanic eruptions and earthquakes that occur on these other plate boundaries I'm highlighting. So, what did we learn from this animation? First, earthquakes and eruptions are happening around the world all of the time. Many of these events occur beneath the surface of the ocean, deep underwater. The animation that we saw showed over 2,000 eruptions occurring from over 300 volcanoes around the world. Secondly, we saw that there was a pattern to where the earthquakes and eruptions tended to occur. It was not randomly distributed across the surface of the Earth, but instead they were concentrated in certain areas, and we correlated those areas where we had more eruptions to the boundaries of tectonic plates. Finally, the last pattern was that the most explosive eruptions and the largest earthquakes occurred at places where we had a particular type of plate boundary, where an ocean plate was subducting beneath a continental plate. Let's make sure that we see this pattern by looking one more time at the maps. First, I'm going to pull over a map of the tectonic plate boundaries. You can see on this map that there are arrows. Where the arrows are pointing away from each other, that means two plates are dividing. Where the arrows are pointing towards each other, that's where two plates are coming together or colliding. The places where plates are colliding, in particular where an ocean plate is colliding with a continental plate, we should see larger eruptions and larger earthquakes. For example, the boundary between the Pacific plate, which is an ocean plate, the North American plate, which is a continental plate, the Eurasian plate, which is a continental plate, we should see along that boundary the largest earthquakes and eruptions. And so, if we pull over the map of the earthquakes and eruptions, we do see that our largest blue circles, red triangles, and yellow circles tend to be in these locations. And so, tune in for future episodes to learn a little bit more about the science of plate tectonics and why we have volcanoes where we do. This video was produced by the Mount St. Helens Institute. We teach about the science and stories of Mount St. Helens and other volcanoes. Learn more on our website, mshinstitute.org.